Hello, so in this video we're going to begin chapter 3. The name of the chapter is the structure of crystalline solids. So you might recall that in the previous chapter we looked at the atom and the structure of an atom, and also the bonds that two or more atoms can form, either ionic bond or molecular bonds, okay, molecules or ions. So here between the atom, all right, so this is a single atom and this is the, let's say this is the material produced. All right, so what is in between? All right, so we know that a very large number of atoms form the material, but what are the details in between? So that is what we're going to look at in this chapter. So the first objective here is to describe what crystalline and non-crystalline materials are. So actually we're going to focus more on crystalline, and also learn how atoms and ions in solids are arranged in space. Okay, so literally how are they arranged? So we're going to identify the basic building blocks of solid materials. Okay, so let's look at some fundamental concepts first. So the definition of crystalline is when atoms are situated in a repeating or periodic array over large atomic distances. So we know that in a material, let's say this is a block of metal. Okay, so these materials, all right, so this block of material are made of repeating array. So that means you can actually break down this block into smaller blocks. All right, and these are repeating itself over the entire size of the material. All right, and this is in a repetitive 3D pattern. So it can go up, it can go to the side, and also in this direction. So what materials will have crystalline structure? So all metals, many ceramics, and some polymers, okay, will have this crystalline structure under normal solidification conditions. So what happens is, first you have the liquid metal. So before they form these blocks of solid material, okay, they go through this process, the solidification process. Actually, we're going to see that in chapter 4. Okay, so they go through this process and form the crystal structure. Right? And we also have the non-crystalline materials, which basically it's the opposite of crystal structure, in which there is no long-range atomic order. So the order is actually quite random compared to crystalline, where it's a repeated order of the same thing. Okay, so that's the difference between crystal and non-crystal. So specific to crystal structure, that these are things that we must know. So crystal structure is actually the way atoms, ions, or molecules are arranged. Now for simplicity, we can just assume that everything is an atom here. Okay, it's a way how they are arranged in space. So this word spatially is coming from space. Okay, how they are arranged in space. And then here we have something called lattice. So lattice is a 3D array. This is basically a lattice. It's an array of points coinciding with atom positions. So if this is an atom, this is the center. So these points are going to coincide with the lattice. You're going to see this better in the next coming slides, and also in a supplementary videos that I have for you here. Okay, so look at this square. You can see that it is coinciding at the center of the atom. All right, this is what it means. And we have what is called the unit cell, which is a subdivided small entity of a crystal structure. So this entire thing that you're seeing in this diagram is a crystal structure, and we can divide it into something called a unit cell. So unit here means one, okay, or a single cell. So the single cell or the unit cell is the smallest basic pattern that you can divide the whole structure into. Okay, it cannot be smaller than this. This is already the most basic form of it. So what you are seeing being repeated here, next to it, and underneath it, and also to the back, is the same cube over and over again. Okay, so that is the whole concept of the crystal structure. Now, there are three types of structures that we're going to look at. Actually, there are more than that, but we're going to look at these three. The first is face-centered cubic. Okay, the face-centered cubic, this is the structure. You can assume that all these are atoms being arranged. And if you take only one portion, you take a unit cell out. Okay, you cut this structure and you take only the cube that we see here. This is what we are going to get. Okay, this is what we're going to get. And if you shrink the atoms here, actually you can see how many atoms are involved in one cube. Alright, you can see that there are atoms in the corner of the cubes, 4 at the top and 4 at the bottom, and also on the face. So a cube will have 6 faces, right? There's 6 sides to a cube. So on each face you will have this half atom. Okay, you have it on this face, this face, this face, and of course on the 3 faces that we don't see. So that is the face-centered cubic. Okay, the videos that I'm going to give after this one will definitely help you to understand more on the crystal structures. Okay, there'll be some animations, so please watch that after this one. So what else do we want to know about the FCC? It contains an equivalent of 4 atoms. So that means of course, you're seeing more atoms here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 atoms here. But these are not whole atoms. If you enlarge it, as in the second diagram, you will see that these are not whole atoms. This is only 1/8. This one is 1/8 of an atom. Okay, you take a sphere, you cut it into 2 and then further cut it into 4 sides and you have 8 pieces. So this is only 1/8 of an atom. Same goes to every corner atoms here. And we have half atom on the faces. Okay, so that's 6 of half atoms and 8 of 1/8 of an atom will be equivalent to 3. This is equivalent to 1. You get a total of 4 atoms. So this is what it means. And the relation of the atomic radius r and the unit cell length. So each cell being a cube will have a side A. A. Okay, all around is we just call it A. That's the length of the cube. Okay, and the radius of the spheres or of the atoms is labeled r. So here we have one radius. Okay, and this is also a radius, another radius, another radius. So on this face alone, we will have 4 radius. So you can take out the triangle. Here is 4r, this is A, and this is A. Okay, so from this relation, of course, this is 90 degrees, so we can develop this equation. So if you were to expand this and get A in terms of r, you will get this equation. Okay, so that's 2a squared equals to 16r squared. A equals to a squared equals to 8r squared. Therefore, A 2 square root 2 r squared. Alright, so we get this, same as this. And next is the coordination number equals to 12. So coordination number is the nearest neighbor or touching atoms. So you will see this more clearly. I'm not going to explain this here. You'll see it in the next videos. Okay. And finally, another thing that we should know about the structure is that there's something called atomic packing factor. Okay, here the APF is 0.74. What it means is volume of the atoms in the cell over the volume of the cell. So in a way it's a ratio, volume of the atoms over the volume of the cell or the cube. Okay, so if you look at this number, it means that only 74% of the cube's volume is filled with atom. So how is that? It's because the atoms being spherical, there's a lot of empty spaces. So of course, spheres cannot completely fill in spaces, right? Because you'll see a gap. Even in 2D, if you arrange circles as closely as possible, you will still have this empty space that is not able to fill. So same goes with the spheres. Alright, so volume of all the atoms combined divided by volume of the cell, and you get the APF. So that is the face-centered cubic. Next we have the body-centered cubic BCC. So this is easier to remember. In the center of the cube, if you take out this cube, you will have one whole atom at the center. Okay, and the corners are filled with also 1/8 of an atom. Okay, so if you shrink the atoms, this is what you're gonna see. So there are less atoms involved here. This is the whole atom, 1, and these are 1/8 of an atom. So how many atoms, how many equivalent atoms do we have here? So we have 2 equivalent atoms. So one whole atom at the center, and at the corners we have 8 corners, and each is 1/8 of an atom. So this is 1, this is another one. We have a total of 2. Okay, so the relation of the atomic radius R and the unit cell length A. So I'm just going to brief you on this. Okay, I will give you an exercise maybe in the next class on this, but there's a tip. Alright, so in the previous example, let's go back to that. In the previous example, we could easily take this triangle on the face out and bring it here and figure out the relation between the side of the cube and the radius of the atom, because on this face you have all the radius one after another, meaning that on this face the radius is full, there's no gap between the space. Okay, so we are able to come up with this 4R. But here there's a problem. You can't take the similar triangle because on the face you actually don't see this whole atom at the center. So if you were to take out the face, okay, let's say we take out the face, you will only see this. Alright, and yes, we know this is A, but we do not know what the remainder is. You don't know what the gap is. This might be R, okay, but we don't know what the gap is. So we can't use this face to determine the relation between the length A of the cube and the radius of each atom. So what we do instead is we take the diagonal across the cube. Alright, so here we have one side, and then at the bottom we take this, and then we take this. So we take that triangle. Okay, in this triangle you have atoms filling up this line. Okay, so I'm going to draw that here as well, all the way to this corner. Okay, so you see that first we have to figure out this side. This is A, and then this will be your 4R. So we need to figure this one out first. This is easy because we have A, and you can easily determine this. Okay, I'm not going to elaborate. Eventually they will get this. This is the relation between A and R. And the coordination number, again, let's wait for that video so that you understand what it is, and then you can come back here and understand the coordination number. The atomic packing factor, so there's only 68% of the cube that is filled up with atoms. Okay, so volume of atom over the volume of the cube is only 68%. So that is on the BCC. Now, the last one is the hexagonal Closepacked, okay, or HCP. So this is a bit different because the unit cell is not a cube. Alright, it's not a cube, it's shaped of a hexagon. Right? And let's see if you can determine how many equivalent atoms are in here. Okay, so this diagram, based on this, you can see that there are 3 whole atoms that you see here. Okay, and I had an argument from a student saying that behind this there's another one. Okay, but no, you can clearly see that based on this diagram. See, there's one here. Oh, it's the same color. Hang on. Okay, so we have 1 atom, 2 atom, and 3 atoms here being whole. 1, 2, 3. Okay, so we have 3 whole atoms, and then at the top, look at this. Okay, this one, and everything is the same at the bottom. So we have half atom, the count of 2, and then at each corner, okay, at each corner here we have 1, 2, 3, 4, 5, 6, another 6 at the bottom, that's 12 times, this is a sphere or a circle cut into 3. So that's 1 over 6. Because you have a sphere, first you cut it into 2. Top and bottom. And then this one is further divided into 3 parts. Okay, so that's 1/6 of an atom. So here is 3. This is 1. And here is another 2. So a total of 6 atoms involved. Okay, so equivalent 6 atoms. And again, coordination number, watch the video after this. And the APF is the same as the APF for FCC that you saw first. Alright, so I'm going to end the video here. Please make sure you watch the coming videos.